SwayamPrabha. Digital India. Educated India.
We're doing some simple problem, which as a part of our connected bodies analysis. So we almost have finished it. I'll just finish it with a few comments. Okay, so we have done this problem, and in particular, we're doing this. The acceleration analysis was, we finished it. I just want to draw the acceleration diagram. And here, so this slider is moving on link DE, while the point C is fixed to on the link 1. So the acceleration of C can be found out from link 1, which we have said consisting of two components, C with A so we did this, and we did it using IJ, but I want to put another directly knowing omega 1 and alpha 1. So I'll just put it directly as 3 square .5657, so that is the length So this is theta, and theta is 45 degrees. And this is 4 multiplied by so that will turn out to be okay. So that's 45 degrees. And from link 2 point of view, the acceleration of C, I'll directly write it. So it is C prime a component, the tangential component, and so we write it as relative acceleration, and one more is the Coriolis. So these are the 3 components, so which you have done. I'll write it down here. So the normal is after calculating omega 2, so we know that it's omega 2 square or C prime with respect to D So these various components, I'll write it down here. So simplifying, omega 2, we did the analysis. So the velocity analysis was gave omega 2 as 3 radians. VREL was so this is much more comfortable writing down the directions and writing down the magnitudes. So finally, this acceleration of C from this side, we have the first one is the normal component of this C prime, which was on dE. So what is the normal acceleration? So that's 3.6. And then the other part, we do not know the tangential acceleration. I mean, the angular acceleration alpha 2 is not known, but we know that it should be multiplied by the value here. Okay, so these are the first 2 components. And the relative velocity component, I mean relative acceleration component, the magnitude is not known, but we know that it's horizontal. We are assuming it to be towards the right, but it may change later depending upon the direction. So final solution. And finally, we have the Coriolis component. So the Coriolis is twice omega 2 VREL. We know omega 2, we know VREL, we know how much it is. So the magnitude is here is 7.2. So the direction, so the magnitude is twice, omega 2 is 3 and multiplied by 1.2. So that will give you same 0.2. So what is the direction of this one? So the direction of this one is, this is VREL and omega 2 is like this, right? So it is nothing but the cross product of K cross VREL. So we have VREL here and this is going inside, and then if you take a cross product of these two, okay, then it will be going, right? So it will be, it's inside here, okay. So if you take a cross product of that, then it will be in this direction, okay, K cross VREL. So that is, I'll tell you a few words of that again. So that is the direction. So there is another nice way of doing it, is the direction of the Coriolis here is nothing but you have VREL here, turn it through 90 degrees in the direction of omega 2. So this is nothing but the Coriolis here is nothing but here, if I write it. So the magnitude is omega 2 VREL. So this is the magnitude, and the direction is the VREL turn through, this is what your cross product is actually, through 90 degrees in the direction of omega 2. Okay, so here omega 2 is going clockwise, and then you have a VREL, sorry, yeah. So the magnitude is, because since these two are 90 degrees to each other, so the magnitude is this much, and the direction is VREL turned through 90 degrees in the direction of omega 2. So that's how, so you have here and turn through 90 degrees and in the direction of clockwise. So this is how the 7.2 comes. So this way, actually, this turns out to be much easier than you were following the vector algebra using IJKs. Of course, that's always is how mathematically it is done, but so this is how you can quickly arrive at the magnitudes. So once you have this, so on one side you have this, okay, from the link 1, on the other side link 2, this is the one. So those two should be same, and once you make them equal, so you can equating this, I think I call this as, so this is 3 and velocity analysis. So using 3 and 4, so you can make them horizontal, or you can make them vertical, or you can even make them in any other direction, okay. In fact, I told the other method also. So in fact, the whole thing can be written as a polar form, vector form, and then you can solve it. So in any case, so I'll leave that for you. And the solution for this one will be, the solution for this one will be, if you solve it, then ARL, you get it as is 1.6 meters per second square, and it turned out to be positive. So that means that whatever assumption we made was okay, and alpha 2 turned out to be -5 radians per second. So this is how you can. So why I have written it in this vectorial form is it's amenable to draw a vector diagram. Okay, I'll just remove this part and I'll draw the diagram here. So the diagram here is that, I'll remove this part. So the diagram here is that so this is the acceleration diagram. So in this acceleration diagram, so what we start on one side, this is completely known. So which means that we have, this is the first part, okay, acceleration of c, and then this is origin, as well as it also represents 2 points, A and B. So if I write it small letters for these things, okay. And then we have this one, so this is at 45 degrees. So this part here is, shall I put the numbers? I think I'll put the numbers, or, okay. So this is AC, the normal component. This is AC, the tangential component. And together we get C. So this point is C. And then on this side, so what we use first is that the known quantities. So 3.6 here. .6 here. So this is the first component. 2 and 3 and 4. So this is the 3.6 part. Okay, first component. And then the second and third are little unknown. So what we do here is that, I think I'll put this one a little longer, though it's not really, it's actually shorter. So this is shorter than this one, so I have to put that. And then after that you have 7.2. So this is 1, this is 4. This is actually the Coriolis. So this is first one, AC prime, the normal component. And then after that we have 2 here. Rel is not known either. And also add this one. This is vertical. So what we do is that so joining these two. So joining these two should be and going up here. So this is okay. So this is the 3 component, which is rel, and then this is the this is 0.4 times alpha. This is the 4th component. I'm sorry, this is the 2. So this is various components which you can add here, and then you can draw this polygon. So this is so if you draw this, so you can even very easily from this diagram also you can very easily see that this you can even solve using this. So a semi-graphical approach. So this is also is very convenient. And then I didn't draw the velocity analysis. So maybe velocity analysis could have been velocity diagram. If I just draw it here. So just like we are done here, so what we do here is, this is the axis and this is the origin here. And here, this is omega 1. So the velocity of, this is velocity of C from this. And then what we have is that from here, from 2, so you have a vertical okay, and this is velocity of C prime, and to which we have to add VREL. So this is the C prime and this is C. Okay, understand? So here this is a velocity analysis, in which case, so this is at some angle theta here. So what it very clearly also shows, yeah, so from here also we can very easily see, so this is known here or using omega 1, and this also tells you that the velocity of C prime here is downward. So that means that this point C prime is moving downward here. So this is the velocity diagram which I was trying to complete here so that your understanding becomes better, is that this is the X and Y and this is the origin here. So this point here also happens to be A and B. The velocities of, this is the image of AB. In fact, this ABC everywhere, whatever you have, so these are the velocity images of various points. So, and similarly here, C prime to C will give you the relative velocity. So obviously this also tells you that C is moving in the rightward direction. Okay, so that way you can really understand the problem much better. Okay. Yeah. And also I was telling, for example, if in the last class I was even telling that the geometric image and velocity image are similar. So for example, if you want to find out E, for example, okay, if you want to find out what is the velocity of E, can you find out? Maybe let us say it is twice. Okay, so once you draw this one, so the E point is nothing but, say, let us say twice that of C prime. So that means that if C prime is here, so if I just extend it from here, so I will get E here. By any chance, if you have another linkage here, imagine that you have another linkage attached to this one. So let us say, so another linkage is attached to this one, like this one. So what you need to do is that you go to E. From E, probably you can find out what F is. And for example, here, so you can even draw from E, you can even draw an F and find out what is the velocity there. Okay. Okay. So you can even, that way you can go on extending this velocity and acceleration diagrams to find out many other points as well. So I think this gives you enough idea into solving various points. So we have been doing these rotating frames for quite some time now, either as a simple point which is having a motion in the rotating frame, or now what we have done is that how to apply that knowledge to the connected bodies. Okay. In fact, yesterday I was even showing how to do the shaping mechanisms, how to do that, because it's a two mechanisms which are at, one is a rotating frames application, the other one using ordinary crank and connecting rod. So I think we did enough kinematic analysis and we had to move on to the other topics. So we just have another 10-12 lectures before the semester ends. So let's move. So the next topic is the kinetics. So kinetics of one thing is that we want to go to rigid body. This is our aim. But before that, before we derive any relationships, any of this rigid body, so we assume rigid body is made up of a system of particles. Because all our this Newton's laws and all that, they are enunciated for a particle. So we have to understand how they can be applied to a particle and how they can be extended to a number of particles, n being infinity. Then we apply the constraints of a rigid body. That means that the particles distance remain same during the ensuing motion. So we apply that and then make that into a rigid body. So for some time, we are going to consider the kinetics, that relationship between force and motion for a system of particles. Then we extend this one, we put some constraints so that it becomes a rigid body. So for this moment, there are a number of particles here. And let us say these are a number of particles here enclosed by this one. And then what we would like to do is that, so we have say a say ith particle here. So let us say this is the ith particle, and it is being acted upon by a force. So there are a lot of forces acting on various particles, and let us say the ith particle is acted upon by a force Fi. But let us also see that this is, though they seem to be, the particles are independent, but then they can apply forces on each other in a mutual manner. So let us see. So there are a mutual internal forces act on each pair. On each pair of particles. So what we mean by that is that, so let us consider the ith particle here, and let us say we also have a jth particle here. So we have a Phi, let me call this as external force, okay, and then these internal forces between the particles will be along the line here. Let us say it is maybe attraction or maybe even repulsion. And this is mutual. So this we call as Fij. So these are internal forces here, and then J may be having an external force. And I goes from 1 to n. So what we would like to do here is that if you want to, we'll start with force and acceleration relationship for a particle, and then we sum it up. So using this, so if ith particle has an acceleration AI, and let's also put some then to start with, we'll put the forces as what? external, and these are internal forces. Yeah. So this is the relationship between the forces acting on ith particle, and these are all vectorial quantities, right? So what we have here is that this may not be just one force. There are a number of forces here. So as far as ith particle is concerned, so this gives you all the forces. So like this, so we have a relationship between, so I ranges from 1 to n. So that means that, so you can start with F1 and F1J. So like this we have so I put down for n particles starting with one particle to Fi, Fj and Fn here. So the thing here is that if you sum it up, summing up all the forces, so we get some simplified relationship. Yeah, summing up all equations. So what we get here is that we have to add all these external forces, right? Right, F1, F2, Fi, Fij. But then there is one interesting thing here is that there are internal forces which are here depicted by small f, and these forces occur in pair. So there is an Fij here and there's an Fji, so they are equal and opposite. So all these internal forces act in pairs, equal and opposite. So if you sum it up, so then they all become 0. And then here we have so this is how it looks like, right? So this is just a note here, all internal forces act in pairs, equal and opposite, and their sum equal to 0. Okay, so this is the interesting part here. So that means that when you consider the system of particles, so all external forces, okay, added up, then will be equal to mass times acceleration. Okay, so this is the important part here. So this is first our inference that internal forces get cancelled when you consider all the particles together. Okay, so like this, we will further simplify this by looking at, so this MIAI, let's look at this MIAI, which can be written as Mi d square by dt square of the position vector. So let us say that the I here is position vector Ri. So ith particle has Ri position vector, and this is a summation. So this can be simplified since Mi is constant, so we can even take that out. So this second derivative of the time is taken out because Mi is anyway constant. So this is how it looks like. So this is, we can further simplify this one, that Mi Ri by using the concept of center of mass. So the center of mass, if you recall, the position of center of mass, say G, is defined as Mi Ri divided by the Mi. So that is where G is. So that means that if you add all these position vectors multiplied by the mass, so then you will get a G here, the position vector whose position vector is defined by this one. So this is how we define the center of mass. Okay. So this is, you know pretty well that the center of mass may be a particle, may not be a particle. It might even be just in vacuum. So just like you have a circle here and its mass is center is in the center. So like that, so we can find out how the number of exercises are there, how to calculate the various center of masses. And this can even be made into a continuum form also. So this, for example, if you have say some odd looking just as a matter of completeness here, the Rg, if you have a continuum, so then it's nothing but a summation here, integral is nothing but R dm divided by df total mass. So this is, you can even put it as 2 coordinates. Okay, so that is parallelly, we keep doing something continuum distribution as well. So you can even, instead of writing this as a discrete summation, we can even write it as a summation over a continuum region. So, okay, so if you have this one, so then what we can write is that using the center of mass definition, so we have d square by dt square, and this is nothing but mass m times R. So where m is the total mass. Of the system of particles. So like this, so we can now complete this, the both sides of the equation. So that means that the summation of all the external forces is equal to mass times okay. So this is the first set of equation. So without considering the relative portions of this one, what we are saying here is that the center of mass moves as if all the mass is concentrated there and all the forces are acting there. So that means that all these things can be, yeah. So what I was telling is that, so the implication of this equation is that, so if when I have a number of particles like this one, so you have a center of mass G here. So now these forces are acting on each particle separately, and if they are moving, obviously G is also moving. Sorry. So the moment of G is as if all the mass is concentrated at the location of G and all the forces are, so that means that this is equivalent to so all the mass is there and so all the mass is concentrated here and this is G. Okay, so this is a major simplification, and so this gives you the location of G at any time. Now we also have another very important thing is that how these particles relative to G are rotating. So that is not said here, right? So we are just only said that all the mass is there and the G is moving as if all the forces are acting there. That's fine. But what about the relative location? Is there any rotation? Obviously, right? So the particles are independent and seem to be also can have rotation. Okay. So how do we take care of that? So to take care of that, so we have the rotational part, which is given by the angular momentum. Okay, so we have to consider the angular momentum or moment, so moment of linear momentum. So for example, we have linear momentum defined by G, and Gi is Mi Vi, right? Yeah, this is the linear momentum, and this linear momentum, you can sum it up. Okay, so the total momentum, total linear momentum is nothing but Gi. So actually the other important part here is that moment of momentum. So angular momentum is nothing but moment of momentum. Moment of linear momentum. Okay, so what does that mean? So we have a linear momentum here given by Gi, and if you take its moment about some point, then we will get the angular momentum about that point. So angular momentum, since you are talking about moment of linear momentum, so this is about some point, So this is angular momentum about some point, right? So how do we evaluate this? So there are which point we take, about which we want to take the moment is there are many ways of doing it. So it can even be simply the origin, it can even be some point, an important point like G, or it may even be some arbitrary point, some P. So now let's look at, there are several ways of taking moments. such as, so let's take moment about, say, origin to start with. Okay, so if you take, we know how to take the, we'll represent it by h. So h, the angular momentum about origin O, is nothing but, so let us see here. So if you have this gi as the linear momentum, and if you want to take the moment about some point, let us say O, so then it is nothing but the taking the cross product Ri cross gi, and we might even take a summation here for the whole system of particles, right? So we can even say here it is Ri cross gi here. Okay, so this is how we write Ri cross Mi Vi. Okay, so now I think we'll continue here. There's a lot of algebra, and then what we need to convert this Vi into derivative of Ri, and we would like to bring the concept of the center of mass also, and then we will we have to derive. There are many important other moment about the other ones also, like the G is a very important point, and then it has many implications, so we are going to see. So for the moment I think we'll stop here.